Next up, we have Hooman presenting, who is also a doctoral researcher in ERBE and ABC at Loughborough University. Hooman has worked in the HVAC industry for 8 years with a master's in mechanical engineering, previously researching concentrated solar collectors and hot water cylinders for solar, water and space heating applications with 3 published articles. Let's welcome Hooman to the stage.
Good evening, everyone. I think this is my 5th time talking about gray box modeling, so I hope it's not boring for you. As you know, I'm working on the applicability of gray box modeling technique on passive house buildings in the UK. So just as a quick reminder, we all use modeling, and we know that modeling is widely used in building energy research. And in the classical sense, like George talked a lot, we used some kind of modeling. We can call it the white box approach, which, requires detailed physical knowledge of the building, such as geometry, construction, infiltration rate, occupancy profile, information about the HVAC system detail, and stuff like that. And then we need detailed mathematical models for calculating transient and transfer processes involved in the building and predict, for example, or calculate indoor temperature or HVAC energy and so on. Examples include design builder, energy plus, analysis, and so on. But as we had a discussion, just John explained for us that there are some uncertainties associated with this white box approach. And also some other concerns, for example, because with the emergence of some new technologies, building-related technologies, actually there are some new challenges that we didn't have before. And these new challenges actually demand us to come up with some new solutions and techniques for modeling. For example, consider district heating or nanoscale modeling or grid integration or advanced HVAC control, which you need to predict what comes next, like model predictive control. In these scenarios, actually, we need, for all these applications, we need reliable and fast modeling tools. They should be reliable and fast to formulate and to implement. In this case, maybe the white box approach, maybe it's not the best option we have. So the challenge is to actually, I think I missed something. So we have to think about other maybe options to handle these challenges. And actually there is a solution, and people found out that the data-driven modeling techniques actually work very well for the challenges I mentioned. And there's a growing interest in the application of data-driven modeling in building energy research. But what we do mean by data-driven modeling? Actually, these modelings are based and developed using the measured data of building after they are occupied, real data. So because of that, buildings reflect the actual building thermodynamics and give more accurate prediction of building response because they are using the real data of the building. And I don't know why. No. Okay, never mind. And they are, as I mentioned, they are often simple, easy to formulate, and require less parameterization. It means you need less parameters in these models, and usually they have less computation time. For all these reasons, they are becoming more popular. But the question is that from where actually we can find all those operational data we need to create data-driven models. Actually, the good news is that with the wide adoption of building automation systems and Internet of Things in buildings, especially modern buildings, actually we are collecting and gathering more and more of operational data, which we can use to inform data-driven modeling. So I mean, more data is available, so we have a better chance to create and develop data-driven models. One of the common data-driven modeling techniques, which is black box, and usually we hear about it all the time, is actually uses machine learning algorithm as a main approach. What does it mean? That in black box approach, which is mainly based on machine learning, we don't know, and actually we don't care about the physics of the system. The only thing we have is some historical data or some information about the behavior of the system in the past. And then we use this data and using a machine learning algorithms from the simplest one to the most advanced ones. We just analyze this data and try to find patterns in the historical data. And based on those patterns, we try to predict what comes next. But there's also another approach, which we call it gray box modeling, which in gray box modeling, we use some kind of prior knowledge or basics of the system is known to us. And actually, we come up with a simple model that reflects some of the physical characteristics of the system. And then we use the measured data to inform or estimate the model parameters. So then I say we have some prior knowledge of the system. It shares the feature with white box modeling that is all based on the physics of the system. And then I say we use the measured data to actually calibrate the model. It means that it has something in common with black box. So that's why actually we call it gray box, because this approach is intermediate stage between black and white box. And in table, we can compare some of the features of gray box. As you can see, it compares some of the features of black box and white box. For example, in white box and gray box, in both of them, we have a mathematical model. In white box and gray box, in both of them, the model, the parameters have more or less physical meaning. But in the black box and gray box, in both of them, actually, we use operational data to estimate the parameters. In black box, no physical knowledge actually is needed, and parameters do not have any physical meaning. So you can see gray box actually lies between black and white box approach. Okay. So just an illustrative example that how gray box modeling works. The most common approach in gray box modeling in building is a method they call it RC modeling or thermal networks, in which we try to represent the building and heat transfer processes, something like an electrical network, which we call it thermal network. Imagine we want to model this zone. So we assume that all the indoor air is lumped in one node. We call it TI. And we assume that this air inside this room, for example, has some thermal capacity. It can store heat. So it has some thermal capacity. We should it's CI. And then, as a just illustrative example, we can assume that all the building structure, building envelope, floor, wall, ceiling, are all lumped in another node with a temperature TE. And of course, the building envelope has a capacity for storing thermal energy. So also we have some CE for the thermal storage of the building. Then we have solar radiation, we have indoor heat gain, and this is outdoor temperature. And then you can see the indoor node and outdoor node actually are connected with some thermal resistances, which is very actually easy to understand and imagine. So the next step is after from actually constructing this thermal network, we apply energy balance on the indoor air temperature and all other nodes that have thermal storage. In this example, we have just building envelope and indoor temperature. So if you have applied energy balance equation on these two nodes, we come up with these two equations. That's why we call this gray box. Now I like to apply the definition of gray box modeling on these simple equations. First of all, you see we have a simple model. So we have some prior knowledge of the physics of the system. So we have some simple mathematical model, and we have some parameters. You can see the ones with red colors are the parameters of the model. So these parameters, actually, you can either calculate them directly if you have a knowledge of the physical properties of the building, or you can calibrate them using the measured data. So you can not only calculate these parameters directly like a white box approach, you can use measurements to calibrate these parameters. That's why it is actually called gray box. So as the next step, as I said, in this system, we have three inputs: outdoor temperature, solar radiation, and indoor heat generation, let's say. These are input of the system, which are measured. Then we have some outputs: indoor air temperature and building envelope temperature. These are output of this system, which should be calculated by solving those system of differential equations. And the rest you can see with the red color. These are model parameters, this system, which should be calibrated. And by calibration, we mean that after calculating TI, we compare the TI for each time step and compare it with the measured TI. So we change or modify or adjust these model parameters so that the square error between measured TI and calculated TR minimized. Okay, that is actually the theory of gray box modeling. Oops. Okay, so now in this PhD, what I'm going to do, I want to apply this gray box modeling on this passive house building on our campus, a Sport Park Pavilion 4, which is built on a passive house. This is an example of a low energy building in Loughborough University. I want to apply this gray box modeling in this low energy building example to actually answer two questions. Can I use this gray box modeling to estimate the thermal properties of this building, as I mentioned in the previous slide? Because those parameters are supposed to have physical meanings. So can we use gray box modeling in this type of building to actually get some information about the building properties? And can we use gray box modeling to predict indoor air temperature and energy demand of this building? Gray box modeling is widely used, and there are many examples of application of gray box modeling in the literature. For example, Vanda, my supervisor, already showed that in her thesis, PhD thesis, that gray box modeling works good, very well in UK dwellings, but in low energy buildings, particularly with different characteristics, very high level of insulation, very airtight envelope, this technique has not been investigated sufficiently. Because these buildings have a different characteristic, the application of this gray box modeling in these buildings still remains what? Unclear. So as a starting point, I have created a kind of, I call it base model, In this model, as you pay attention, I try to include all the elements of this model actually is applied on the ground floor of the building, which does not have any natural ventilation and occupancy. It was an unoccupied building during the experiment. So I'm creating the base model, and as I move forward, I try to simplify this model, So as the starting point, if you can see, for example, this node actually represents the floor of the ground floor with the temperature TF. This is the ground temperature. This node actually represents ceiling. This is temperature of the first floor, and this is for wall. And RFAS is for windows and ventilation panels which do not have a thermal mass. And RAI is the thermal resistance of infiltration. RAHU is the actually thermal resistance between mechanical ventilation, supply air. So this is a relatively complex model. So I'm starting from here, and I want to first test this model on the ground floor, and then try to, one at a time, just lump these elements together and simplify the model, and finally see which model with which level of detail is good enough for our purpose. And with the same method, I explained to you, we can come up with a set of differential equations if we add energy balance on all the nodes with thermal mass, the floor, ceiling, walls, and indoor air. And then the model inputs are these ones: ambient temperature, solar radiation, indoor heat gain, temperature of the upper floor, ground floor temperature, ventilation temperature, supply temperature, and ventilation supply flow rate. And these are the model parameters, the red ones. And finally, the outputs are the green color ones, the temperature of the indoor air and the building elements. So, as the first thing, I want to see that can this modeling technique actually provides me with some insight about the thermal characteristics of the building. In other words, is it capable of provide some meaningful values for these parameters after calibration? So in order to investigate this, first of all, I'm using the building construction data to calculate these model parameters first. Okay, just like what we do in a white box approach. CI is the thermal mass of the indoor air, CW is the thermal mass of the wall. So each of them, actually, if you sit down, you can calculate all of them. And directly, if you have enough information about the building construction, then I have to identify a plausible range for these parameters. Each of these parameters, if I calculate the value directly, how much I should expect this parameter to change in real world. Maybe identify the uncertainty associated with this parameter, should be fine or not. But ultimately, I have to construct some kind of research space like that, which θ0 is the calculated value of these parameters, and theta is the estimated value. So theta should be, confined in an interval that P is something I should decide about that. Gives you somehow, how far you can deviate from the calculated value. And then after establish this parameter range, I have to calibrate the model, and with these calibrated values, try to predict the indoor temperature to see how this model performs in model parameter estimation and indoor temperature. So the first step in my modeling is to running some summer experiment, which we used 1 week in September 2023. This is the outdoor temperature measured on Loughborough campus. As you can see in this week, starting of September 4 and ending of September 12, actually we have some kind of heat wave week with high level of ambient temperature. So what I'm going to do as the first attempt is to use the data of the pre-heat wave. Let's call this heat wave week, and this is the pre-heat wave week. So the first thing I'm going to do is to train the model using the pre-heat wave week, and then apply the model to the heat wave week, the data of the heat wave week, and see that if I train the model with pre-heat wave week, can I predict the indoor temperature in the heat wave week? So let's see what happens. This is actually the training results. This is the pre-heat wave week, and you see that you can compare the measured data and calibrated data, and I used E0.9 for constructing the search space. Currently, temporarily, this 0.9 just comes from literature, and people actually didn't bring solid or very strong justification why they use 0.9 or 0.8. But just as something, to start working, I use this, but later I should, decide about the best value for P. After training the model, I applied it on the heat wave week, and that's the result, You can see for the first 3 days, it predicts better, but as we move forward, the error becomes bigger and bigger, and that's because, I use the a numerical method for integrating this system. And currently I'm using Euler method, which means as you marching in time, the error of the calculation becomes bigger and bigger and bigger. Anyway, but let's take a look at the parameter values. In terms of predictions, if you are interested in calibration or comparing models and stuff like that, you know that RMSE and CDRMSE are the indexes that usually are used. But for training and testing, the prediction of the model is not bad, so. Of course, it can be improved, but more interestingly is the parameter estimation. You see, you have the list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 parameters, and that's hugely a lot for an RC model. This is the calculated value for parameters, and based on P 0.9, this is the lower and upper limit for these parameters, and I use the calculated values for initialization of parameters, and this is the calibrated values, and these are the errors. Given that the P was equal to 0.9, it is interesting to see that calibration for most of the parameters found us for me an extreme value. It tries just to push the boundaries, So what I'm concluding here at this point is that I calculate the parameter values, use the physical knowledge, and construct the space around those parameters and allow parameters to change by 90%. Okay, this calibration could not actually identify parameters really close to the calculated values, and I see as some kind of problem for parameter estimation in this experiment. And first of all, I hope, as I mentioned, because we have 12 parameters here, and if you remember, when I mentioned we have maybe just 3 or 4 inputs in this model, so this is a kind of over-parameterization problem. The gray box models, if you increase the number of parameters, you are very likely, to come up with some result like this. The calibration cannot give you the parameters in a plausible range. So as a first hope, I try to, to launch that. Let's go to the next slide. So as a next step, what should I do? First, I have to refine the parameter range, find the better value for P to establish a, well-defined space for calibration, and then try to lump those different building components together to make my model more simplified and reduce the number of parameters to try to avoid over-parameterization. And then repeat the experiments, so hopefully next time I can show you the parameters with much more feasible or plausible values. And later I should include natural ventilation in my experiment, because this model was applied on the ground floor. In the upper floors during the summer experiment, we had natural ventilation. So I should include natural ventilation and see how the gray box model can capture natural ventilation, and also apply this model later to winter data set to see how this model actually can predict heating energy demand of this low energy building. These are the steps actually I should take to complete my experiments. And thank you.